Greetings and welcome to another installment of Quantslob. This is 25 in our basic application series. Before we start here, I wanted to mention a couple of you have asked why we don't tape with a live audience. Well, it turns out we've tried this in the past, but it didn't seem like anyone in the audience, really applauded or laughed at any of the jokes. In fact, I recall I even noticed a number of our studio audience taking a nap during the taping. So we figured, why go to the extra trouble and the added expense? Anyway, this time around, we're going to keep rolling with part 6 of our practical series on hypothesis testing of a single proportion, picking up right where we left off in part 5. If you want to enjoy all the thrills and chills, I suggest you watch this mini-series in full. You can find it playlisted under the Quantslob channel playlist tab. So let's do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. Now, observing that this coin seems quite typical and knowing nothing else about it, we fashion a statistical test. We use the normal approximation, a standard normal or Gaussian distribution to approximate the sampling distribution of our sample statistic proportion of heads. When we set our significance level to 0.02, or simply 1 in 50, our critical region under the standard normal model of our null sampling distribution is any value of our test stat that's less than or equal to negative 2.3 or greater than or equal to positive 2.3. Now, in our little made-up experiment, we flipped this coin 50 times and got 30 heads. Our observed sample proportion is therefore 3/5. We plug our result along with our hypothetical value for the true population proportion of heads, along with our sample size, and we end up with a calculated observed test statistic of about 1.41. Since this test stat, this particular value we obtained, does not fall in the critical region, we do not reject the null hypothesis, or we fail to reject the null. In our little make-believe experiment with this coin, our 50 flips or trials, we did not encounter sufficient statistical evidence to overturn the assumption that the coin is fair. So let's imagine another example. Same basic setup as before with our coin. We assume that the coin is fair, and we are interested in whether or not it is, in fact, loaded. Again, we set our significance level to 1 in 50. We still use, of course, the normal approximation, so our critical region is the same. However, let's say that in our experiment, we flipped it not 50 times, but rather 200 times, and these flips produced 120 heads. Now, the first thing to point out here is that our proportion of heads is the same as before, as with our original example, 3/5. This means that in calculating our test statistic, the difference between our observation and our hypothetical parameter value is the same as before, 1/10. What has changed, however, is our sample size, the number of trials. This directly affects our standard error. Increasing the sample size shrinks the standard error. And so here, in this example, our test statistic does, in fact, land in the critical region, and we hence reject the null hypothesis. That is, we conclude that the coin is loaded. In our little make-believe experiment this time with our coin, our 200 flips or trials, we did, in fact, encounter sufficient statistical evidence to overturn the assumption that the coin is fair. Just so we can say we did it, our test stat is about 2.83 here. Our p-value is the area of our normal PDF that corresponds to the combined regions here in the two thin gold regions here in the tails. This is a rather small number, about 1 in 215, something like that. So while we're at it, let's run through another very different looking example. So for this example, we're going to bring back an old Quantslob friend, our beloved bolt making machine here, a machine which makes bolts. So isn't that nice? We got our bolt making machine. Remember that, to harkening back to our foundational series. Okay, so let's say we have a batch run of 200,000 bolts, and so this is going to be our population of interest. To each bolt, of course, we have numerous attributes. But for the sake of this example, let's say we're interested in the two-level categorical attribute has high ultimate tensile strength. Basically, does the bolt possess especially high strength? Now, if you're a big fan of fasteners, and I mean, after all, who isn't? You'll know UTS can also stand for Unified Thread Standard, so we could also QC test our bolts based on the standard tolerance. It doesn't really matter. This is just an example. Okay, so anyway, if our bolt making machine is working correctly, 4/5 of the bolts it produces will have high UTS. This is our default value, and so we hypothesize that this is the proportion in our run of 200,000 bolts. We cannot test all 200,000 bolts in our population. In fact, some fastener QC tests actually destroy the component, so it's completely impractical. What we can do, however, is select through a mechanism of random selection a subset or a sample of 200 and test them. Now, in our coin flipping experiment, we wanted to detect loadedness of the coin, and that could mean that either heads or tails were favored. With a QC test, we are usually more focused on a particular region in our parameter space. In particular, our concern is that our beloved bolt-making machine may not be performing as it should, or if you prefer from a business perspective, that this batch run of 200,000 bolts may not be up to the standard of excellence of which our customers have come to expect. This is reflected in our alternative hypothesis. Here, our research inquiry is concerned with the prospect that the true population proportion of high UTS bolts is less than 4/5. If so, we may have to downgrade the specification and reduce the price of this batch run, and maybe even have our bolt making machine inspected and serviced. So for this test, let's set our significance level to something a little bit more traditional. Let's say 1 in 20. Remember the basic logic of our critical region here, a space that contains values that are improbable given that our null hypothesis is true, and also potentially highly probable if the alternative is true. Our critical region is hence concentrated here on the left tail out here of our normal model. So let's say, for the sake of example, after we randomly select our 200 bolts and perform our quality test, that 165 have high UTS. So now we plug our hypothetical parameter value 4/5, our sample size 200, and our sample statistic 33/40 into our trusty equation and get something about, 0.8839. Here, our test statistic does not land in the critical region, and we hence fail to reject the null hypothesis. That is, we do not conclude our bolt-making machine is underperforming, or if you like, we do not conclude that our batch run is substandard. Our p-value here is the area under our normal PDF that corresponds to the region less than or equal to about 0.8839. Be reminded that we know this is our p-value region because it contains values that are rare if the null hypothesis is true, and also contains values that may be very likely if the alternative is true, and must also include our actual observation. Whatever you do, do not miss our action-packed mini-series grand finale, and that's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. Don't forget to stay tuned for more Quantslob.